Okay, so for this module, we'll have centrifugation or the centrifugal separation. First, let's just look at the figure of what centrifugation is, and let's look at the definition. It basically deals with the separation of particles from a fluid by means of centrifugal forces acting on the particles. They're used for particles that cannot be settled easily by gravity settling. So when you look here at the bottom, you can see the natural sedimentation or the gravity settling. For example, you have a slurry. You will have to wait until time t where it could settle, and then you can observe a separation. However, for some particles where you have, for example, emulsions or you have suspensions, it would be better if you apply a bit of external force. So this one can be applied centrifugal separation because it gives faster results. So as per the name, it implies we use centrifugal force. So there is a rotation. So you can also observe the separation in here. When you look at the figure, you can see here that the slurry, the liquid that contains the solid particles, is fed into the separator. And then you will notice, like, from the green to the yellow, this is the light phase that will be left out as it rotates. And then the unseparated liquid there contains heavier materials. And then the heavy phase would be here that can be separated. And lastly, at the walls, you can see there the sediments will be attached against the walls. Some of the applications of centrifugal separators are separation of cream from whole milk, separation of cellular materials, just like in blood, the plasma, beers, vegetable oils, fish, protein concentrate, and fruit juices, in the drying of crystals, separation of emulsions into liquids and solid liquids, removal of dust particles from air. So you can see the inlet is usually in the middle, and then it rotates. And what happens is the solid particles will be at the walls. Some of the principles of centrifugal separation, as I have said, you will apply here rotational action. And then there's centripetal force, of course. And what you'll notice is that the centripetal force is towards the center. And then that the velocity is always tangent and perpendicular to the centripetal force that's tangent to the circumference of the circle. We can see here that the rate of settling of a particle or the rate of separation of two immiscible liquids is increased many times by the application of the centrifugal field or the centrifugal force, much more than that of gravity. Because of course, you will apply how many times gravity for that. For the parts, of course, the liquid that is on top is what you call the supernatant liquid. So for centrifugal acceleration, if we can recall from our physics, centrifugal acceleration is r times omega squared, where omega is the angular velocity. It should be in radians per second. Of course, r is the radius, and mass. If you multiply the acceleration by the mass, you'll have the force. In this case, it's the centrifugal force. So here you can see the velocity, as I have said, is perpendicular to the force. Here, of course, if the acceleration is towards there, towards the center, the force is towards the center as well. So in comparison, this is a summary. For gravity settling or natural settling, you can say that F is equal to mg, acceleration is constant, that's gravity. It's in the direction of the Earth, so downwards. Equilibrium velocity is reached, and then the terminal velocity is given by this equation. We've already had this in lesson 6 and lesson 7.1, where ut is the terminal velocity, dp is the particle diameter, this is the density of the particle, density of the fluid, acceleration due to gravity, and this is the viscosity, the dynamic viscosity. Whereas in comparison, the centrifugal force mr omega squared, the acceleration increases with increasing radius. The acceleration increases with increasing omega. And then away from the axis of rotation, all the time. And then equilibrium velocity is never reached. However, the instantaneous velocity can be solved. You'll notice here that there is a relationship between the terminal velocity and the instantaneous velocity for centrifugal action. It's r omega squared divided by g. So basically, ut just divided by g and then multiply by r omega squared. Isn't it that this one has units of g as well, the r omega squared? So in turn, they would have the same units. That's just velocity. Some of the formulas that are important here are, of course, the Stokes law formulas. You've already encountered this. So U is basically change of distance or change of displacement with respect to time. It's given by this formula, the terminal velocity. And then the time can be solved by using 18 mu all over omega squared, density of the particle minus density of the fluid, diameter of the particle squared, ln of Rb over Ra. So what are those R's that we are speaking of? By the way, the T here, take note, that's usually what you call the residence time. Let's look at the schematic diagram here. So in here, this is the centrifuge. The feed, of course, is being fed in here in the middle, and then it would go outwards as it starts rotating. And then the R1, take note of that's the radial distance from the center or from the axis of rotation to the free liquid surface. And then the furthest one, R2, is the radius of the centrifuge bowl, the whole bowl. RA is the distance of particle at any time A, this one. And then RB is the distance of the particle at the end of its residence time. And then B here is the height of your bowl. And also, you can see here that this is the surface of the liquid. And then the trajectory, the direction of the particle, because it's being fed on top at the middle. It would go down here and then it would start at the bottom and then being spun and then it would go out towards the wall. Again, for the residence time here, 18 mu over omega squared, raw particle minus raw fluid, dp squared ln Rb over Ra. First, let's go to some of the important terms in here. Critical diameter or cut diameter. This is known as the diameter of the particle that reaches half the distance between R1 and R2. So basically, between R1 and R2, critical diameter would be found somewhere here in the middle. And the critical diameter or the cut diameter, a particle of this size moves a distance of R1 minus R2 all over 2 during the settling period. If the particle of diameter dpc is to be removed, it must reach the bowl wall in the available time. So sometimes in the formulas that you can see, like here earlier, you'll see RA, RB, R1, R2. This one can be simplified actually. So how is it simplified? If you can say that you give enough time such that RB here reaches the wall, RB is equal to R2, and that RA would be halfway. It's the critical point. R1 plus R2 over 2. What happens is that um, the RA and the RB can be replaced by R2 and R1 plus R2 all over 2. So instead of having this formula here, the one with RA, RB, you can just take note of this. So in this case, you know what omega is, you know what B is, that's the height of the bowl, you know what these parts are. The only thing that's new to us is the QC. QC is what you call the volumetric flow rate corresponding to the cut diameter. Sometimes I call it the critical flow rate. So do take note that at this flow rate, most particles whose diameters are larger than the cut diameter will be eliminated already by the centrifuge. And most particles having smaller cut diameters will not be eliminated but just remain in the liquid. Okay. So let's go to some examples. I'll just solve two examples. The first example is the one in Geankoplis. A viscous solution containing particles with density 1461 kilograms per cubic meter is to be clarified by centrifugation. The solution, density of the fluid, 801 kilograms per cubic meter, and its viscosity is 100 centipoise or centipoise. The centrifuge has a bowl with radius of 0.02225 meters, radius 1 of 0.00716 meters, and a height of B is 0.19 centimeters. You're asked to calculate the critical particle diameter of the largest particles in the exit stream, given that the rotation is 23,000 revolutions per minute and that the flow rate at this point is 0.002832 cubic meters per hour. So I already wrote here the formulas and then the parts, so in order to guide us as well. So let's write the given. We were given the density of the particle as 1461 kilograms per cubic meters. And then the density of the fluid is given to be 801 kilograms per cubic meters. And you're also given the viscosity, the dynamic viscosity. So mu is equal to 100 Cp. So this one is actually equal to 0.1 Pascal second. And then you're given the radii. Radius 2, 0. So the bigger radius is 0.02225. Radius 1 is given to be 0.00716 meters. Height B is 0.1970. What's required is the cut diameter. So this one, when the revolution is 23,000 rev per minute and at Q of 0.002832 cubic meters per hour. For the formula, we already have the B. The omega, we can solve for that. The density of the particle, density of the fluid. This is what we're solving for, the dPc. We already have R1, R2, so no problem with that. This one, we already have. We have the Q, because here, since you're given, calculate the critical particle diameter. So that means this happens at the critical flow rate. So we can see that this one here is QC, critical flow rate already. So you're already given this one. All we have to do is plug in everything. So let's just convert first those things that can be converted. Revolutions per minute. So 1 rev is 2 pi rad over 60 seconds. This one would be 2408.55 rad per second, or let's just use 2410 rad per second. And then this one, it has to be in terms of seconds. So 1 hour is 3,600 seconds, 87 times 10 to the negative 7 cubic meters per second. Okay, so maybe we can already solve by plugging in everything. 7.87 times 10 to the negative 7 is equal to pi times B is 0.1970 times omega 2410 squared times density is 1461 minus 801. There's already in kilograms and cubic meters. So 1461 and 801. So we don't have a problem with that. And then next is dp c squared all over 18 mu. This is already in Pascal second. 0.1 Pascal second is kilogram per meter second. And then multiplied by R2 squared. R2 is 0.02225 minus 0.00716 squared all over ln of 2 times 0.02225 all over 0.02225 plus 0.00716. It's basically just plugging in the values. So here, what you'll have is 7.46 times 10 to the negative 7 meters, or I can say 0.746 times 10 to the negative 6 meters, or 0.746 micrometers is your diameter, the cut particle size diameter, right? That's your answer for the problem. Now, let's go to another concept. You already know what QC is, the critical flow rate. Now, sometimes there is a need because if we apply things at a laboratory scale and then we would want to scale it up. So we need to get what you call the sigma values here. So this is the formula for the sigma values. Basically, QC, you already know the formula, is equal to 2 times the terminal velocity times sigma. The sigma is the area of gravitational settler that will have the same sedimentation characteristics as the centrifuge for the same feed rate. That's why in here, you correlate them by equating Q1 over sigma 1 is equal to Q2 over sigma 2. So basically, we can scale it up using this relationship. So let's go to another problem. Problem number 2 again for Geankoplis. For the conditions given in the first example, this is the first example, do as follows. Calculate the sigma value, and a new centrifuge having the following dimensions is to be used. R2, 0.0445, R1, 0.01432, B, 0.394. Earlier, if you remember, 0.02225, this is double the radius. And then 0.00716, again, this is double. The B, if you can recall, the B that we have is 0.1970. This one is double again, right? But the number of revolutions, instead of 23,000, it's 26,000. You're asked to calculate the new sigma value for this one and then the scale up flow rate. So what will be the flow rate compared to the first one that we had? So in this case, using the formula sigma, what's being asked here? Letter A, calculate the sigma value. So letter A, required sigma value for problem number 1. So you're given the dimensions here. So let's just apply. So again here, sigma for number 1, 2410 squared, that's omega squared, pi times 1970.02225 squared minus 0.00716 squared all over 2 times 9.81 ln of 2.02225 divided by 0.02225 plus 0.00716, you'll get the sigma 1. So this is the characteristic for the first centrifuge, 196.5 square meters. So we already have an answer for letter A. For letter B, you're asked a new centrifuge having following dimensions. So calculate the new sigma and what would be the new flow rate. So given the following information, I already wrote them here, the R1, the R2B, and the new number of revolutions. So here I calculated first the omega. So it has to be in rad per second. And do take note that the earlier answer that we had for Q1, that's 7.87 times 10 to the negative 7 cubic meters per second. So I'll solve first for the sigma. Again, this is the formula on the right. The omega squared pi 0.394, and then radius 2 squared minus radius 1 squared all over 2g ln 2 times radius 2 all over radius 2 plus radius 1. So you'll get a sigma 2 of 2007 square meters. Now, you're asked to scale up. So this is one of the answers already. You're asked to solve for the sigma, so this is one of the answers. And then in scaling it up, let's get the ratio of sigma and the flow rate. So flow rate over sigma 1, flow rate over sigma of 2. So Q, you'll notice, is 8.038 times 10 to the negative 6 cubic meters per hour, or 0.03 cubic meters per second. So comparing it with that one, right? So definitely you'll notice that there is much uh, improvement. It increases by a lot. So that ends the lesson. Thank you very much.